vector to do an image similarity, right? So as you saw earlier, each image is represented as a set of 3 channels, and each channel has intensities between 0 to 255 scale for each cell, each pixel within the image. So here in this particular example, you have one image which is a 10 by 10 size. So for each channel, you have 10 into 10, 100 cells, and we can represent this as a vector and a single dimensional vector by flattening out these 3 channels. So let's start with red channel. So red channel, you start writing 100, 59, 242, etc. up to all the way to 159. Then the next value is just represents row 2, starting with 222, 198, 147, so on and so forth. Let me also designate it in the diagram so that it's very clear. So this is row 1, then this is row 2, right? So on and so forth. So all the rows you are representing just one after another as one cell, and you repeat that till you finish the red channel, right? So here starting blue channel is starting, the next one once the red is finished, and again you just start writing the values one after another for all rows, and this represents the blue channel, right? And this represents, similarly you can put green channel. So the first thing you need to represent in order to represent the first thing you need to do to represent image as a vector is to flatten out all the two-dimensional arrays for each channel into a single dimensional array just by putting the values one after another. So in terms of size, so if this was array of 10 by 10, this is array of 10 by 10, this array of 10 by 10. So each channel will contribute 100 elements, right? So total size of the final vector would be 300 into 1. So this is how you represent one image uh, as a vector. Again, depending on the size of the image, your dimensions will vary. For example, if the image is 20 by 20, so each image will have 400, each channel will have 400 cells. So into 3 it will be 1200, right? 1200 total cells. So the size of the image varies depending upon the problem, but the gist is you convert basically a multi-dimensional image array into a single dimensional image array before you process. So here is another example. So an image of one aeroplane you represent again as a 300 by 1 dimensional array, and again another aeroplane you can represent as another array. So this is what computer sees, right? The computer sees just image as an array of numbers, or you can also call it as a vector. So each image represents a 300 dimensional array vector if the size is 10 by 10. Again, if the image size is different, your vector size would be different. So this is how you represent image as a vector. Now if you want to calculate similarity, there are several algorithms available. Again, you are basically computing the distance, and we learned about several techniques like Euclidean distance, cosine similarity, etc., etc. Now let's take a look at how you can apply these algorithms for an image set. So let's say you are given an image of a dog, and the dog does not have a label associated with it, and the goal is to find the label for this image, right? And we are going to use the algorithm called KNN, also known as K nearest neighbor. Now before giving this algorithm, our computer has been trained on few images of pandas, cats and dogs, right? So computer already knows what a vector looks like for an image panda, and it has also computed internally and kept that distance. So it knows what distance looks like for panda. Similarly, we have images of a cat and we have images of dogs, right? So which we have already given the computer along with the labels. So computer knows vectors for each of these images on the corner of this slide, and also known the labels for these images. So the KNN algorithm, what is first we need to identify it's a voting system, right? So what it does is first uh, we need to tell oh, the algorithm that how many neighbors you want to compute. So basically and you can give, let's say, 3, 4 or whatever neighbors you want to compute, and majority, and then ask each one of them to vote, right? And then you just compute majority votes, and then you declare that I am similar to the majority of my neighbors. So basically the whole idea behind KNN is if you want me to tell you who you are, you need to tell me who your neighbors are, and then I can tell you who you are. So I am basically deriving the your label based on what your neighbors are telling me. That's the basic concept behind it. So in KNN, what you do is you have all vectors for all the images, right? So you first compute vector of the new image which does not have a label in this particular dog, and you compute a distance for the existing set of dog images, right? And then you find nearest one of them. Then you compute the image of this dog with all the images of cat, and then you similarly do that for panda. And then what you do is you compute the let's say the neighbor size is 5. You sort your neighbors. You create the neighbors array based on the distance and sort them based on the distance. So you compute 5 nearest neighbors based on their distance from the image under consideration. So in this particular case, I have calculated the distance of my current image with every other image in my corpus, and I have created a list, and I have sorted the list based on the distance, and then I have replaced the distance by associated labels. So in this particular case, the number of neighbors are 5, sorted in the order of ascending distance. So I have 3 neighbors closer, which are out of 5 close neighbors. I have 3 neighbors which are designated as dog, 1 cat, and panda. Then I compute the number of votes, and here it says dog is 3, cat is 1, and panda is 1. So since dog is 3, majority of my neighbors are dog, so the KNN algorithm declares that the image is also dog. That's how nearest neighbor algorithm works, and we will also walk through a code to understand this in more detail.